Okay, let's get started. So, okay, the title has started. So last week we started how to put the share code at other locations. We are still on the stack, but in environment variables and also command line arguments. So within there, they are still get injected into the victim program's address space. So, but so far we have been overwriting the return address on the stack. We are overwriting the vulnerable return address functions return address on the stack. So today we are going to study something a little bit more difficult. So let's say we do not have the ability to overwrite any return address on the stack. We only have the ability to overwrite the saved EBP or RBP on the stack. So you can say that even that we still will be able to hijack a program. It's just you need to understand each instruction, how it works. So you can say why it still cracks a program. So the attack we're going to study today is called the frame pointer attack, because we're going to override the saved EBP or RBP. So basically, we're not overwriting the current vulnerable function's return address, but somehow we change the upper level function's return address. For example, we'll be saying a lot of Overflow there. Overflow is a vulnerable function. Overflow is called by main function. We're not going to override the return address of Overflow directly. However, we can override the return address of the main function for that. Okay, so here is overflow. Okay, guys. So for folks online, I'm sorry about that. I don't know why I will muted myself there. Anyway, so so this is the program. All the program I'm showing you in the class, they are quite simple, but you can imagine in real world, the vulnerabilities will be buried in sometimes millions lines of code. So in this class, what I'm showing you is just a very several lines of code, and there is a vulnerability, so it will be very easy to identify those. In real world, it's very challenging to identify those. So we have a main function here, a standard main function, and the main function checks how many command line arguments are there. 2, otherwise it returns. So we know from this source code, we know we're supposed to input through command line arguments. Then it calls the vulnerable function Overflow. Overflow has one parameter. Then it has the parameter is actually the second command line argument there. It has a local variable buffer, 4 bytes at a SQL level. After that, there is a memory copy. So this is another vulnerable function we're looking at. We have been looking at a string copy, gets. So this is another one, memory copy. So memory copy is just the copy content from one memory location to another. We copy from the second command line arguments to the buffer. Okay. However, we're copying 12 bytes. We know that at a buffer here is only 4 bytes. So it's very possible there is a buffer overflow here. But we don't know how many bytes we're overflowing. By the way, the memory copy will copy exactly 12 bytes. Okay, so this is different from string copy. String copy stops at where you find a 0. This is also different from gets. Gets stops at where you have a new line, but you will add a new line and a 0 at the end. So this one copies exactly 12 bytes. Okay, so this is a disassembly code from this Overflow. Let's take a look. First, we have this under BR32. Like I said, this is an instruction. So far, we don't care about. It's a security feature, but we don't care about it. Then it has the beginning has push EBP, move ESP to EBP as a standard prologue of function. Then push EBX, subtract the 4 bytes from ESP, then call another function here. So this is somehow related to reallocatable code. So this part you don't need to care about why we're doing it. Actually, it's not related to the security bug we're looking at here. Then there is an add some number to the EAX. So this is related to this one. So we don't care about that. So after that, it's what's related to the security bug here. We have a push OC, which is 12 here. Then we push another EBP plus 8. So EBP plus 8 is what? Is basically the parameter, right? Because EBP points to the saved EBP, EBP plus 4 plus points to the return address, EBP plus 8 points to the first argument. In this case, the first argument is the address of the second command line argument, that's string, right? So then we load effective address EBP minus 8 to EBX, then push EBX. So now we push the 3 items onto the stack. Those 3 items are the parameters of memory copy, right? So like I said, we push things from right to left. So we push 12 first, OC, then we push the address of P. We push P, which is the address of the command line of the string. Then we push the destination, the buffer address. So from here we can say the buffer is located at EBP minus 8. Okay. So even though C code level buffer is 4 bytes, actually the buffer is 8 bytes at a binary level. EBP minus 8. Then we have saved EBP return address with the first argument. So all 3 are pushed onto the stack. Then there's another move EAX to EDX. This one doesn't really matter. Yeah, go ahead. The stack. This is the first push, right? This is a second. Here is the second push. Here is the third push. Push what? We're not pushing the buffer, we're pushing the address of the buffer to the stack. Yeah. That is in EDX. And the buffer that is EBP minus 8. Yeah. Hex decimal 8, the same thing, right? So minus 8. Now after that, here we have a move EAX to EBX. Doesn't really matter here, doesn't really change anything. Then after that, we have the memory copy function call. Okay. So this memory copy is guaranteed to copy 12 bytes to the program. Then after that, it will balance the stack, move 0 to EAX. The reason to move 0 to EAX is because this function returns 0, and we always put the return value in EAX. Now after that, we have a leave, then return, we go back to the main function. Okay. So if we run this program, what will happen? Oops. When we run this program, what will happen? If we do not give it any argument, it will just return, don't do anything. If we give it argument, no matter how much we give, what will happen? It will get segment fault, even if we only get 2 bytes here, right? Because even if we are only providing 2 bytes here, the function, the program here will copy 12 bytes. We don't know what are the other 10 bytes there. It's just garbage on the stack, and that will be copied to the stack, overwrite the saved EBP. We're not going to overwrite the return, okay? But saved EBP eventually will trigger a segment fault in our program. So go back here. So later let's do a debug to see why exactly it triggers the segment fault. Okay. So let's take a look at what exactly happens here. First I use the slides, then we do a demo debug to see why it triggers segment fault. So like I said here, let's say our input are, let's assume we input 12 8s, okay, character 8, 12, each 8 is 1 byte. So what happens is we're going to overwrite this whole 12 bytes, but we're not going to overwrite the return address, right? So the saved EBP will be 4 8s, the buffer will be 8 8s, okay? Then after everything, we are going to return. Eventually, the Overflow function will return. When the Overflow returns, we know that ESP points to the return address. So the return will be successful because we didn't touch the return address. But the EBP will be 4 8s because the leave here has a pop EBP, right? So when it returns to the main function, EBP will be 4 8s. However, ESP, yeah, because let's assume our input is 12 8s, okay? Just assume that. It can be anything else, okay? We just put, what I'm talking is, we are doing this. We're doing this, okay? This is our input. Then let's figure out what will happen when we give input like that. So the return will be successful because we didn't touch the return address. So next, we will go to the main function. We will go to the instruction after the core Overflow function, right? This is where we're at. And at this point, ESP will point to, before executing this instruction, ESP will actually point to P, not return, because we have a return instruction. The return instruction will move ESP 4 bytes out, right? Okay, so after that, we have this instruction and 4 bytes to ESP. So ESP will point to 4 bytes higher than P now, okay? The purpose to do that is to actually balance the stack, because the reason we have P here is because we want to call the Overflow function, which takes a parameter. Since we pushed something to the stack, later we need to balance the stack, push it with decrement 4 bytes. Now we need to add 4 bytes back. Then we move 0 to EAX. The only reason to do that is the main function also returns 0. So we're setting up the return value. After that, we have another return, a leave and a return. And this is where things get very interesting. Remember, everything we have here, 12 bytes here, are still all 8s. No one touched that, right? Now we have leave. Leave is basically 2 instructions: move EBP to ESP and pop EBP. That's it. So since the first instruction is move EBP to ESP, and we already know that EBP is 8s, the ESP will also be 4 8s. So both of them, the value will be 4 8s. Okay. The second one is we're going to pop EBP. Pop EBP means pop whatever ESP points to on the stack to EBP. So the problem here is ESP points to 4 8s. Now we do this one, we're going to pop whatever we treat, now we treat 4 8s of the address, which is 41, 41, 41, something like that. We will pop whatever there is to EBP. We don't know the value, and there is a risk that the 41, 41, 41 may not be a valid address. So this is the first point we may have a segment fault. right? We could have a segment fault here. Let's say we do not have segment fault. Let's say if the pop is successful. What is the pop's side effect? The pop will move ESP up 4 bytes. So ESP previously has a value of 4As. Now it moves up 4 bytes. So ESP will be 3As and E. That will be the new value of ESP, okay? Then after that, if there's no segment fault, we are going to execute the return instruction. What does return instruction do? The return instruction will just pop whatever ESP points to EIP, right? So basically, the return instruction will just pop whatever is that 3AE back into EIP. That is how it works. And this is our second chance to have a segment fault, because we don't really control what is this at this place. It may jump to some very random place. Okay. What you can see here in this example, our goal is to control EIP. Our goal is to somehow point EIP to our share code to execute our malicious function. And our share code, okay, we can, like what we started last week, we can put that in the environment variables. We don't have to inject it here directly. So how can we control this EIP to make it point to our share code? So that's what we are going to do. Go ahead. If you do not, okay, remember, so if you do not give 12 bytes, you can only give 4 bytes. Then whatever after that 4 bytes, you don't know the value, but that will be copied to here. Exactly. So it will still corrupt the saved EBP, eventually trigger segment fault. But you do not control those bytes. Yeah. Okay. So let's debug this program a little bit to see what's going on there. Let's say we have GDB this program. We're going to set a function breakpoint on main function. Make it a little bit larger. We are going to run this program with 12 A's, sorry. So there's 12 A's. So right now we are at the main function. We're going to set a breakpoint in the Overflow. We continue. Now we should be in Overflow. Okay. Now we do a SI. We enter Overflow. Now we're in Overflow. We know where the variable function is the memory copy, right? So let's set a breakpoint there. And we continue. Okay. Now we are going to do the memory copy. So let's see how it overwrites things. We examine the stack. Let's examine 4x from EBP. Okay. So this is what the EBP looks like, or we can do EBP minus 8. Let's see. So EBP minus 8 is where our buffer is, right? So our buffer right now, there is just 8 bytes of zeros, nothing there. Then we have saved EBP, which is this value. This is saved EBP, and this is a return address. You can see this address is 5655 something. Look at this value. This is in the code section. So this address is actually part of the main function. That's a return address. After that, we have some other value we don't really care about. So now we're going to execute the call with the NI here. We're still in Overflow. Now we point to now EIP is here. So now if we examine the stack is already overwritten, right? Now we in that stack, you can say we overwrite 12 bytes. We overwrite the buffer, which is 8 bytes. We overwrite saved EBP. Now we give it 4 8s, 41, 41, 41. Return address now changed. Okay. So now we keep executing this instruction. Let's go to, oops, there is an EBP minor. Okay, this one may trigger fault. Let's see. Okay, didn't trigger any problem there. Good. So now we're at leave. Okay, this is where things get interesting. Let's examine the stack again. What is leave again? Leave is move EBP to ESP, right? So right now, ESP is this value. EBP is this value. So we are going to move EBP. Let's do print. Let's do the line here. Now we check the load value again. So EB. So let's see. So it does two things. First one is leave is pulp, move EBP to ESP, then pulp EBP. That's why we get the EBP basically get the saved EBP value, right? So EBP get it after saved EBP value, EBP is 40, 40, 40, 41, 41, 40. Okay. So ESP points to basically ESP still points to the stack, which is higher here. Okay. So now the next instruction we're going to execute will be return. Because we didn't change the return address, ESP right now still points to the return address. Because of this, we will be successfully returned to the main function. Okay. Now we successfully return to the main function. No segment fault yet. Everything looks okay. After that, we have this add. We have this move, doesn't matter. Now we have another leave. This is where things get, where we have errors. So now EBP points to this. Like I said, leave basically are two instructions, move EBP to ESP. So after leave, ESP will have the value 41, 41, 41, right? Then will be pulp EBP. So we're getting whatever is at that 41 address. Let's take a look if that address has a valid address. So we can examine 4 bytes at that address. 41, 41, 41, 41. Oh, that's not a valid address. Okay, that is not a valid address, so we may get a segment fault here because we may get a segment fault because of the dereference of that address. Okay, so see, we get a segment fault because we dereference address that doesn't exist. But you get the idea here. What if the value is not 4x? It's something we can control. Okay. So the question here is, how can we already know what the vulnerability is, what the bug is. We're going to exploit this bug so we can eventually make the EIP point to our shortcut. So how do we do that? I will give you, let's use this slide to explain that. Let's assume whatever the buffer's address is 4 p's. Well, it doesn't really make sense, right? I mean, but let's assume that's an address. Then if we say, in this attack, we can only overwrite 12 bytes anyway. So it's not going to be super difficult to write an exploit because you can only write 12 bytes anyway, right? But it's a little bit difficult to understand because you need to understand what's exactly going on. Let's say this address is 4 piece, and if we write the saved EBP address of 4 piece, then what will happen is EIP eventually, not here. Remember previously, we override 4/8. Then EIP eventually evacuates from 4/8 plus 4 bytes. Okay. So whatever you override there plus 4, EIP will dereference from there. Then what if we get the buffer's address? We know the buffer's address. We say buffer's address is 4 piece. We'll move that 4 piece into the same EBP. Then what will the EIP difference from? The EIP will difference from those 4 piece plus 4, which is this new of the buffer. The high 4 bytes of the buffer. And that is what you can control. Okay? So that is where you want to put your share code address. Does that make sense? Because you need to eventually make the EIP point to your share code address. But how do you put the share code address onto the stack? And this is how we put that. This is one way to do that. There are many other ways. So let's see, how do we, but in the server, there's another problem is, not going to say, you don't know exactly where the buffer is, right? Even if you need to debug that, that is the address without giving the different address. So how do you get that address? You can guess. You can guess byte by byte. Eventually, it will be successful. So to make this challenge a little bit easier, what I did is the vulnerable program actually will print out. So in this challenge, the program will actually print out where the buffer is for you. So you don't need to do the guessing. Okay. So how do we construct the exploit here? The first thing is share code. We need to put the share code onto the stack. So let's put the share code onto the stack. I think I can use last week's slides. Share code. Which one is it? Oh, this one. Here is a white space. That's why I'm removing it. There's a lot of white space. There's a lot of white space. Okay, looks good. We put the share code onto the stack in environment variables, and we need to find out where it is, right? So we do get 32 spots. Right. So this is where our share code is, but remember, this is where the whole thing is, which include the leading S code equal sign. Okay. So basically, for the real share code, you need to add several bytes. We have a huge mob slider here, so you can add 20, 30, 500 bytes. Doesn't really matter. So after that, the vulnerable program will be. The vulnerable program will take what? Will take command line arguments. So we will have what? We'll have 12 bytes. 12 bytes of payload. So if we do this, what's going on here? Any syntax error here? Why it's not auto-printing anything? What? Oh, yeah, here, right? Here should be a code. Yeah, all right. Okay. Okay, so another interesting thing is we run this program twice. Once with 2 bytes of input, another time with 12 bytes of input. You can say those two addresses, oh, in this case, they are the same, but not necessarily all the same. Let's say we have a very long ones, it will be different, you see? Because those things, command line arguments are pushed onto the stack. That's why it changes the stack of the variable program. So you can see the buffer's address will be different. Okay, so that's why we first try to put 12 bytes here to get this address. Then we want to have 12 bytes of payload. As I showed in this slide, 12 bytes. The first 4 bytes doesn't really matter. We only need to care about the address of it. The second 4 bytes will have the address of our share code. The third 4 bytes will have the buffer's address. That's our exploit. What? The first 4 bytes don't matter. We're not going to use it. The second 4 bytes are the share code's address, okay, which we already put in the environment variable. The third 4 bytes should be the address of the buffer, okay. So first 4 bytes don't matter. Second 4 bytes. Second 4 byte will be share code address, which is this one, right? So of course we want to add a little bit there. So we have A0, then we can use B0, DC, FF, FF. Then after that we have the buffer's address, which is here, which is 64 D4 FF FF. So that is our exploit. So basically just 8 bytes. But you need to understand why those 8 bytes can trigger the problem. You can say you get a flag. Any questions here? Change which address? Oh, like I sent you. The address I get here for using the get environment 32, that is the exact address of the whole environment variable. Environment variable has 2 parts: name of it, equal sign, and the value. And the whole thing is basically a string. So the first several bytes, they're not really our share code. That's basically the string S code. If we do not change that, so we get into what? Where is that? A0. No, not here. Here. If we do not change that, we go to A0. We're actually executing from here, the S code, not the share code. And here, I don't really know what are these instructions, but anyway, you were well, we get lucky. So S code is not any dangerous instruction there. See this one. Oh, another possibility is the program I give you will actually give the values address, not the names address. I'm not sure. We can debug to figure this out. For example, here, but if we debug it, it will be different. Yeah, it's possible that it's giving you the, for example, let's do 9F. That still works. Interesting. And let me figure out what's going on here. Why this one still works? Well, oh, is this one wrong? BC, FF. Even 8F would work here. 7F will not work. It starts at A0, DC A0, DC F8. Huh, very interesting. What do you guys think? What's going on here? Yes, but we're actually here. We're actually pointing to in front of the knobsled. There must be a lot of garbage there. Must be some garbage there. How come it's not triggering? We cannot be that lucky. I mean, we're talking about almost 32 bytes, right? We cannot get a 32 bytes of a knob and some random location. That's weird. Oh, I think okay, another possibility is this address is actually the address is where this environment variable is at for this program, right? For this program. And when we run this program, there is actually several, maybe 100 bytes off. And because of the off, then we have a huge step. It actually hits the sled. So let's change the your idea. Let's change our share code a little bit. First unset it, so we should not have it. Okay, we don't have this. We don't have it anymore. We are going to reset it. So this time, let's do not have a sled. Now we don't have a sled. It has to be very accurate. Oops, what I'm missing. Oh yeah, missed one here. Okay, so now we get this. It's at this address. Let's try again. So it will be 94. Let's try 94D again. It may not work. Okay, so 94D should not work. We add the 6 more bytes there. So it will be 8, no, sorry, 9.4 will be 9.8, right? So technically, this should work if the stack is the same. But obviously, it's not working because the share code, when we run this program, the share code is not at that location. That's a problem. So that's why the previous one it works is because the share code is not really at that location. It's a several bytes, maybe 100 bytes off, and we have a huge slip. Now we have to exactly hit where that is. And it's not at that location. Okay. Cool. Any questions? Buffer -4? Yeah. Yes, you're right. So in that case, so basically your idea is we're going to put the return address here, right? Then here we say buffer -4. Yeah, that will work. Also, there are other approaches. Here you can only overwrite 12 bytes, but by using environmental variable, you can overwrite a lot of bytes, right? So you can. So this one, you don't have to point it at the buffer. You can point it at your environment variable, but your environment variable doesn't have the your environment variable has a lot of those addresses, those share code address, right? So in that case, your chance of hitting, so basically it's not a knob stack, but it's more like you are putting the same address a lot of times. It's not code, it's just address. You put that on the stack and make it point to there. That will also work. Okay, does that make sense to everyone? That will also increase your chances. Okay, so the same approach should work for 64-bit as well, but you guys can try. So for the next part of the class, I want you guys to hack this one. So I will walk around to show you how this works, because this one is a little bit difficult to understand. Seems easy to hack as long as you understand it works. But for example, you can try if you can do the approach to the address in the share code. Yeah. So a little bit about what we're going to do after this. Next class, what we're going to do is we're going to talk about all kinds of approaches that have been deployed on your current systems to defeat those buffer overflow attacks. So we're going to talk about data execution prevention. So we're talking about, but to bypass that, we're going to do return to libc. You can say every time there is a new attack, then it comes with a new soon someone design a new defense. After that, people design new attack to bypass that defense. They always like this. For example, people proposed the DEP, and that was even embedded in the CPU. Then people discovered we can do return to libc. After we're going to do several examples with return to libc. After return to libc, then we are going to talk about some other defense like shadow stack. This is still a very popular research area. In my lab, we also do shadow stack for different architectures. Then there's another one called the stack cookies. This is also widely used. And for stack cookies, it's still bypassable. So we're going to have several challenges for you to bypass the stack cookies, which require you to write programs to do the guessing this time. Then there are other approaches to rearrange everything on the stack. For example, you have some vulnerable buffer, but what if you place a buffer at other places so you cannot override your return address, those kinds of things. So that's what we're going to do starting from this Wednesday. But now I want you to try to exploit this overflow 6. I'm going to put leave this line here so you can see how to craft your exploit. Okay, we're finished that. We'll stay with all that to answer some questions. Okay, any questions from online folks? Well, I mean, I see someone asking a question, but I don't think this is a question I can explain here. Come to my office hour so we can debug what's going on there. Okay, I'm going to stop sharing and stop the conference.